Okay. Today we will be starting a discussion on 2D finite element problems, but before we go into that, there are a couple of things about one dimensional problems. If we consider the two noded element, in a two noded one dimensional element, which is defined like this, the two nodes, okay, and at this end we have said zeta is equal to -1 and here zeta is equal to 1, and the shape functions, we have taken linear shape functions which had a shape something like this. This is n1 and n2 is something like this. This is node 1 and this is node 2, and we said that u is equal to n1 q1 plus n2 q2, okay, where u is a deformation at any arbitrary point and q1 and q2 are the deformations at the two ends. Okay. Now for n1 we said it will be a linear relationship, n1 is 1 here and 0 at the other end. So this expression was one minus zeta by 2 and n2 was 1 plus zeta by 2. Okay. If you notice in this case, I can also write x to be equal to n1 x1 plus n2 x2. Okay, just to verify this, we have said zeta is equal to 2 times x minus x1 divided by x2 minus x1 minus 1. Okay, this is how we have defined zeta, and n1 and n2 have been defined like this, n1 and this is n2. Okay, if I put the value of n1, n2 and zeta back into this equation, you can verify that x will be equal to n1 x1 plus n2 x2. Okay, and that should be clear otherwise also, because x is a linear combination of x1 and x2. Okay, we have defined zeta to vary linearly between node 1 and node 2. Okay, so x will be equal to n1 x1 plus n2 x2, and whenever we have a situation of the type that u is given by an expression like this and x is also given by a similar expression, okay, such elements are referred to as isoparametric elements or an isoparametric formulation of the problem. Okay, the isoparametric elements or an isoparametric formulation. Okay, that means the location x and the deformation u are given by similar expressions. Okay, such elements are called isoparametric elements. In fact, we will notice that when you go into 2D problems, 2D and higher dimensional problems, we will prefer to use isoparametric elements in a number of situations. Okay, that simplifies the formulation to a certain extent. Okay, we will be seeing in 2-dimensional problems how that happens. If you notice the quadratic elements, where zeta is also defined in a similar manner, and where we said u is equal to n1 q1 plus n2 q2 plus n3 q3. This is not a isoparametric formulation. Okay, because in this case we cannot say, okay, x will not be equal to n1 x1 plus n2 x2 plus n3 x3. Okay, that should be quite obvious, because n1, n2 and n3 are going to be quadratic. Okay, and zeta will be defined in a linear manner. Zeta will be varying linearly along the length of the element. Okay, so this relationship will not be true for 3 noded 1D elements, 1D quadratic elements. Okay, so these elements are not isoparametric. Okay, and the only other thing is that yesterday we were talking of 3 noded quadratic element. Okay, we had done the numbering like 1, 2 and 3, and in this case even if we do the numbering in any other way, okay, if we do the numbering like this or the other way around, eventually it will not make a difference. Okay, the only thing that might that will change is how the global matrix is to be formed. One has to be consistent from the beginning to the end. The numbering, the local numbering, the way it is done, the numbering will not make a difference. One just has to be consistent from the beginning to the end. Okay, and with this we will now go on to 2-dimensional problems. And in 2-dimensional problems, if you have any object like this which is having some boundary conditions and some external forces acting on it, what we will do is we will take any arbitrary point here, okay, the location of this point is, let us say, xy, and we will say that the deformation would be u in the x direction and v in the y direction. Okay, and then we will say that the vector u will be the vector u v transpose. Okay, this is the vector of the two deformations. This vector, this u and this u are different. Okay, this is a vector u and this is a scalar quantity which is a deformation in the x direction. Okay, we might not put this arrow every time, but by the context it should be clear. Okay, then the strain epsilon will be given by epsilon x, epsilon y and lambda xy. There will be 3 terms and this will be the strain vector. Okay, similarly the stresses will be given by sigma will be sigma x, sigma y and tau xy. Okay, as for the forces, the body forces acting on the body, that is volumetric forces, will be Fx, Fy transpose. That means there can be a body force, maybe gravity or maybe magnetic force or some such force acting throughout the body on a per unit volume basis. We will use this notation for that. And then for tractive forces, they will have components of Tx and Ty transpose. Okay. Then the next thing will be epsilon x. Okay, we will say epsilon x will be equal to del u by del x, epsilon y will be equal to del v by del y, and epsilon z, sorry, we are having a 2-dimensional case, so that won't be there, lambda xy will be equal to del u by del y plus del v by del x. Okay, and sigma that is the stress vector will be given by d times epsilon, where epsilon is the strain vector, and d would be given by where nu is the Poisson's ratio. Okay, so if you know epsilon x, epsilon y and lambda xy, we can compute sigma by this relationship. Again, this relationship has been derived directly from basics of solid mechanics. Okay, you have Poisson's ratio which will contribute to the stresses. Okay. Now, with this background, with this notation, we will be solving the two-dimensional problems. The first type of element that we will take is what we call as a three-noded element. If we have a body like this, okay, with some boundary conditions, we divide this body into a set of triangles. Okay, so those triangles might look something like this. Okay, in each of these elements, okay, let us say this is element number 1, this is 2, each of these elements have 3 nodes. Okay, that is one node here, here and here. This is one element number 1. Element number 2 will have 3 nodes, that is this, this and so on. Okay, so if we just consider one element, okay, there are 3 nodes of the element, and for these 3 nodes we will define deformation in the 2 directions as these 2 vectors. Okay, let us say we have some xy system, that is a coordinate system, the origin, this is x direction and this I am saying is the y direction. Now this is the deformation in the x direction, maybe we will call that q1, this maybe we will call that q2, similarly this maybe it will be q3, this will be q4, this is q5 and this is q6. Okay, so you have 3 nodes, and at each node we have deformations both in the x and the y direction. Okay, the x coordinates will be given by x1 y1, x2 y2 and x3 y3. Okay, if we consider any arbitrary point here with coordinates of xy, that will have a deformation in the 2 directions given by u and v. Okay, so now we have got 3 nodes on this element 1, 2 and 3. The deformations, if we write down the deformation vector, the deformation vector would look like q1, q2, q4, q5 and q6. Okay, this is the deformation vector. Okay, so q1 to q6. Since we have 3 nodes, this vector is going to have 6 elements in it. Earlier when we were talking about the one dimensional case, when we had 2 nodes, the element deformation vector had only 2 elements. In a 3 noded element we had only 3 elements in Q. Now in a 3 noded element we will have 6 elements. Okay, okay, it is a column vector. And later on when we talk of the global vector, we will define a global vector Q, which will be like this, which will consist of, let us say, Q1, Q2 till Q2n, okay, where n the total number of nodes. Okay, n is the total number of nodes, and the global deformation vector will be given by this vector. Okay, it will have 2n elements if n is the number of nodes. Okay, so therefore individual location of that won't correspond to a particular node, that will only correspond to deformation in one direction of that node. Okay, and each individual location will normally be referring to that by the term called degree of freedom. Okay, so we will say that this vector has got 2n degrees of freedom. Okay, the term degrees of freedom is basically used because if I consider a complete formulation, okay, that means a figure like this, and it has n nodes, then there are 2n deformations which have to be specified. Okay, the 2n deformations. So we will say that this has got 2n degrees of freedom. Okay. So this is the element deformation vector, this is the global deformation vector. Okay. Now if we consider u, which is a deformation at any arbitrary point. Okay, the x direction deformation at any arbitrary point xy. Now this deformation u will depend on q1, q3 and q5. Okay, we will say it will be a combination of q1, q3 and q5. Okay, because q2, q4 and q6 are the deformations in the y direction, and q1, q3 and q5 are the deformations in the x direction. Okay, so the deformation u will depend on q1, q3 and q5, and we will take it to be a combination of the three. So we will say that u will be equal to n1 q1 plus n2 q3 plus n3 q5. Okay, where n1 into n3 are the shape functions. Okay. Similarly, deformation in the y direction will be given by n1 q2 plus n2 q4 plus n3 q6. Okay, because q2, q4 and q6 are the deformation of the three nodes in the y direction. Okay, and if we write this down in a vector notation, we will say that the vector u will be equal to n times q, which is equal to n1 0, n2 0, n3 0, 0 n1, 0 n2 and 0 n3, this multiplied by the vector q. Okay, the vector q is a column vector of q1 to q6. Okay, I will just write it here, q1 Okay, so the first row multiplied by this column will give us this equation, and the second row multiplied by this column will give us this equation. Okay, and let's say if we put n1 equal to zeta and we put n2 to be equal to eta. Okay, we can put these expressions over here. The third constraint is that n1 plus n2 plus n3 has to be equal to 1 at all locations. Okay, that is because if I consider this element, it's a combination of the three. It need not be linear. Even if it is not linear, it's a combination of the three. That means the deformation at any point is a combination of deformation here, and a deformation here. Okay, so the total weightage of the total weightage we are giving to any of the three has to be 1 at any point. Has to be 1 at all the points. Okay, that means the weightage given to this point plus the weightage given to this point plus the weightage given to this point has to be equal to 1 throughout. Okay, so n1 plus n2 plus n3 will be equal to 1, and therefore we will get n3, we will say n3 will be equal to 1 minus zeta minus eta. Okay, so we will get u to be given by this expression where n1 is zeta, n2 is eta, and n3 is 1 minus zeta minus eta. Okay. Now, right now what we have done is that we have given an expression for u as a function of n1, n2 and n3. Okay, but we haven't yet specified as to which point we are talking of. We haven't yet related n1, n2 and n3 with the x values. Okay, that means if I am taking any particular point over here, I am trying to find out the deformation at this point. Okay, this relationship gives me the relation between u and q as a function of n1, n2 and n3. Okay, but I am yet to relate n1, n2 and n3 with the xy values. Okay, the xy values are the location of this point x and y. I have to specify n1, n2 and n3 as a function of x and y. Okay, so relating these two, what we will do is that we will assume or we will take what I just explained earlier, isoparametric elements or an isoparametric representation. And if we assume an isoparametric representation, we have said u is given by this expression, so x also has to be given by the same expression. So xy will also be equal to n times, let us say, x. Okay, or we can say x will be equal to n1 x1 plus n2 x2 plus n3 x3, and y will be equal to n1 y1 plus n2 y2 plus n3 y3. Yeah. Yeah. Okay, assuming representation to be an isoparametric, this is the way we are defining an element right now. Okay, so x is given by this relationship, y is given by this relationship. Okay, and if you put these values, n1 is zeta, n2 is eta, and so on, I can simplify this further. We will get x to be equal to zeta times x1 plus eta times x2 plus 1 minus zeta minus eta times x3, and y will be equal to zeta times y1 plus eta times y2 plus 1 minus zeta minus eta times y3. Okay, or this system or this set of equations, I will simplify them further and I will get x to be equal to zeta times x1 minus x3 plus eta times x2 minus x3 plus x3. Okay, and this I will write as zeta times x13 plus eta times x23 plus x3. Okay, where x13 x1 minus x3, x23 x2 minus x3. Okay, so this will be equal to x, and similarly I will get y to be equal to zeta times y13 plus eta times y23 plus y3. Okay, so x is given by this, y is given by this relation. Okay, similarly if I write down u and v, I will be getting u to be equal to zeta times q13 plus eta times q15 plus q3, sorry, and v will be equal to zeta times q24 plus eta times q26 plus q6. Okay, this should be quite straightforward. All that I have done is I have put n1 equal to zeta and n2 equal to eta and n3 equal to 1 minus zeta minus eta in these equations. Okay.
Will it be q35 in the first equation of q u here?
Here q35.
Yeah. Because
Let me just check. x13, x23. Is that okay?
yeah.
Yeah, thanks. q35 and this will be q46. Okay, the basic thing is that the deformations in the x direction are q1, q3 and q5, and in the y direction the deformations are q2, q4 and q6. Okay, so this way I have got expressions for x and y and expressions for u and v. Okay, essentially what I am saying with saying now is that if I take any particular point, let's say if I take some value of zeta and some value of eta, okay, zeta and eta are both varying between 0 and 1. Okay, if I take some value of zeta and some value of eta, I can put it in these equations, I will get some value of x and some value of y. Okay, if this is that point xy, then the deformations here are given by these expressions. Okay, so if I take some specific point here, some specific point with some xy values, I will first have to find out the zeta and the eta values over here, and in finding the zeta and the eta values I will have to make use of these equations. Once I find zeta and eta, I will put them back over here and get the values of u and v. Okay, maybe what we can do is we can take a small example just to see how xy and u and v are related. Okay. let's say the coordinates of this point are 1.5, 2. The coordinates of this point are 7, 3.5. The coordinates of this point are 4 and 7. Okay, and at some point here P, whose xy values are given by 3.85, 4.8. Okay, so I know x is equal to zeta times x13 plus eta times x23 plus x3. Okay, and y is equal to zeta times y13 plus eta times y23 plus y3. Okay, so these two equations will give me x as 3.85. So 3.85 is equal to zeta times x13. X13 is x1 minus x3. Okay, that will give me minus 2.5 zeta plus x23 is x2 minus x3. That will give me 3 times eta plus x3, which is 4. Again, similarly from here the y value is 4.8, so I will get 4.8 is equal to minus 5 zeta, which is y13, y1 minus y3, 2 minus 7 is minus 5, plus y23, 3.5 and 7, that will give me minus 3.5 eta and plus y3, which is 7. Okay, so these two equations I can solve them simultaneously. I will get zeta, which is the same as n1, to be equal to 0.3. I will get n2 or eta to be equal to 0.2, and of course n3 I will get will be 1 minus zeta minus eta, which is equal to 0.5. Okay, once I get zeta and eta, if I want to find out the UV values here, okay, that I can find out by the equation. I know n1, n2 and n3, so U is equal to n times Q, that will be equal to n1, which is 0.3, n2 is n2 is 0.2, 0 and 0.5, 0. The second row will be 0, 0.3, 0, 0.2, 0, 0.5, and this is multiplied by the Q column vector, which is Q1, Q2, Q3, Q4, Q5 and Q6. Okay, so this is how we can find the deformations at any arbitrary point inside this element. Okay, so we have U to be equal to n times Q, where n is given by this matrix at this particular point. Is that okay? Any questions up to this point? Okay, what I will stop here now. In the next class we will see how we can relate these deformations, or how we can relate these expressions with the stresses and the strains, and then go on to solve the potential energy expression. Okay, we will take that up in the next class now.